Good morning to all. My name is Aarti and my roll number is 50. This is an audio lecture for visually impaired students on the topic of quantum mechanics basic introduction. Introduction. Classical mechanics. Towards the end of the 19th century, physicists were greatly satisfied that they were able to explain most of the phenomena on the basis of Newton's law of motion and Maxwell's electromagnetic wave theory, according to which energy is emitted or absorbed continuously. The former were used to explain the phenomena related to motion, examples, trajectories of planets, falling stones, etc., and the later to explain the phenomena related to energy transfer. The branch of science based on Newton's law of motion and Maxwell's electromagnetic wave theory to explain phenomena related to motion and energy is known as classical mechanics or Newtonian mechanics. After that failure of classical mechanics was able to explain phenomena related to large objects that are macroscopic particles. However, it fails when applied to small particles such as electrons, atoms, molecules, etc. For example, according to classical mechanics, it should be possible to determine simultaneously the position and velocity momentum of a moving particle, but this is contradicted by the Heisenberg uncertainty principle. Similarly, classical mechanics assumes that the energy is emitted or absorbed continuously, whereas Planck quantum theory postulates that energy is emitted or absorbed not continuously but discontinuously in the form of packets of energy called quanta. Further, the concept of quantum numbers was introduced arbitrarily to explain the atomic spectra. A few phenomena for which the classical mechanics fails to give a satisfactory explanation are black body radiation, photoelectric effect, heat capacity of solids, atomic and molecular spectra, black body and black body radiation. When radiant energy falls on the surface of any body, a part of it is reflected, a part of it is absorbed, and the rest is transmitted. The whole of the energy is not absorbed because generally the surface of ordinary bodies are not perfect absorb- absorbers of radiation. However, if the radiant energy is allowed to fall on the blackened metallic surface or carbon black, it is found that the energy is almost completely absorbed. A body which completely absorbs the radiant energy falling on it is called a perfectly black body. The absorption is found to be more perfect if we take a hollow sphere blackened on the side inside and having a small hole for the entry of the irradiation for the entry of radiation. This is so because any radiation that enters through the hole is reflected over and again by the walls of the sphere till finally it is completely absorbed. The most commonly used black body is the one designed by Ferry. It is hollow double-walled metallic sphere having a conical projection B opposite to the hole H and is coated on the inside with lamp black. The projection helps to avoid any direct reflection as otherwise the body will not act as a black body. Further, a black body is not only a perfect absorber of the radiant energy but is also a perfect radiator. In fact, of all the bodies, the black body irradiates the maximum amount of energy for the given temperature. The radiation thus emitted are called black body radiation. Kirchhoff's law. Though a black body is a perfect absorber as well as a perfect radiator of energy, all other bodies also absorb the radiant energy falling on them as well as emitted. The relation between the energy absorbed and the energy emitted by a body may be obtained qualitatively on the basis of simple experiment. For this experiment, take a hollow enclosure is suppose the walls of this enclosure have been imparted a uniform temperature and then thermally insulated to keep the temperature constant. Now suppose one black ball B and one white ball W are suspended in the enclosure with the help of insulating thread. In the beginning, the whole space inside the enclosure is filled with a radiation emitted by the walls. Further, the walls of the enclosure are continuously emitting as well as absorbing radiation. As the balls can absorb as well as emit radiation, it is found that the balls also acquire the temperature of the enclosure, which remain constant so long as the temperature of enclosure is kept constant. Now the question arises, why the temperature of both the balls is same in spite of the fact that the black ball is good absorber. Evidently, this is due to the fact that the black ball must be a good radiator too. Thus, we conclude that a good absorber is a good radiator, while a poor absorber is a poor radiator. The exact quantitative relationship between the energy absorbed and the energy emitted by a body was put forward by Kirchhoff in 1859. It is called Kirchhoff's law and its status as follows. At any temperature, the ratio of the emissive power of a body to the absorptive power is constant independent of the nature of surface and is equal to the emissive power of a perfectly black body. The term emissive power or emittance implies the energy emitted by the surface per unit time per unit area, whereas the term absorptive power or absorbance or absorptivity is the fraction of incident energy absorbed by the surface per unit time per unit area. Thus, if ES and AS represent the emissive power and absorptive power of a substance, and EB represent the emissive power of a perfectly black body, then according to Kirchhoff's law, ES by AS is equal to EB. Proof of Kirchhoff's law. Kirchhoff's law can be derived a simple manner as follows. Suppose Q is the amount of radiation incident per unit area per second on a body. If AS is the absorptive power of the surface, then the amount of radiation absorbed by the body per unit area per second is equal to AS into Q. If ES represents the emissive power of the surface, then the amount of radiation emitted by the surface per unit area per second is equal to ES. When the body is in thermal equilibrium with the enclosure, amount of radiation emitted by the surface per unit area per second is equal to amount of radiation absorbed by the body per unit area per second. That is, S is equal to AS into Q. For a perfectly black body, AS is equal to AB is equal to 1 and ES may be replaced by EB, where AB and EB represent the absorptive power and the emissive power of a perfectly black body. Thus, we have EB is equal to Q, then ES is equal to AS into EB, or we can also say that ES by AS is equal to EB, where EB is constant, and this equation gives the expression for the Kirchhoff's law. Spectral distribution of black body radiation. With increase in temperature, the energy radiated per unit area per unit time from any surface increases rapidly, and simultaneously the color changes from dull red through cherry red and orange up to a bright white heat. Further, it is observed that at same temperature, the rate of energy emission is much less for a bright metal like platinum than for a dull black surface such as an incandescent carbon filament that is at temperature above 3500 Kelvin. On the basis of experimental studies, Stefan in 1879 showed that the total amount of energy irradiated by a perfectly black body per unit area per unit time is directly proportional to the fourth power of its absolute temperature, that is T. That is where sigma is universal constant, also called Stefan constant. If the energy is expressed in arcs times second and area in square centimeter, its value is 5.6 into 10 raised to power minus 5. The above statement is called Stephen fourth power law or Stephen Boltzmann fourth power law. As a theoretical proof of this law was given by Boltzmann by applying the laws of thermodynamics. The energy emitted by a black body at any temperature does not consist of a single frequency and also not uniformly distributed along the spectrum. Loomer and Pringsheim in 1899 studied experimentally the distribution of energy amongst different wavelengths of the black body spectrum. The black body radiation were obtained by heating a carbon tube electrically. After passing through the slit S1, they were made parallel with the help of a concave reflector mirror M1 and then allowed to fall on the fluorosphere prism to get the spectrum. The radiation after refraction through the prism were focused by another concave mirror M2 and the slit S2 onto a linear bolometer. By gradually rotating the prism, the radiation corresponding to different wavelengths were focused on the bolometer one by one and their intensities measured. By keeping the carbon tube at different temperature, a number of observations were taken between 621 Kelvin to 1646 Kelvin. The curves were then plotted between the monochromatic emittance E lambda along the ordinate and the wavelength along the abscissa for each of the temperatures. Results. Some important results from the curve obtained at particular temperature. The distribution of energy is not uniform among the various wavelengths of the radiation emitted by black body. For each temperature, there is a wavelength lambda m at which energy radiated is maximum. With increase in temperature, the maximum shifts higher but towards lower wavelength. This means that with increase in temperature, EM increases but the corresponding lambda m decreases. Higher the temperature, more pronounced is the maximum. The area under the curve for a particular temperature gives the total energy emitted by the black body per unit area per second for the complete spectrum, that is corresponding to all the wavelengths at that particular temperature. The area under the curve increases with increase of temperature, and it is found that the area is proportional to the fourth power of absolute temperature. As the area under the curve represents the total energy emitted by the black body per unit area per second, hence it be directly proportional to T raised to power 4. This is Stephen Boltzmann law. Thus, the wavelength lambda m for which the emittance of black bodies maximum is inversely proportional to its absolute temperature. This is called Wien displacement law. This law is applicable to explain why the color of visible light radiation changes from red to yellow as the temperature of hot body is increased. After that, photoelectric effect, when a beam of light with frequency equal to or greater than a particular value called threshold frequency is allowed to strike on the surface of metal, electrons are ejected instantaneously from the surface of metal. This effect is called photoelectric effect. Some important observation are the electron are ejected only if the frequency of incident light is equal to or greater than a minimum value called threshold frequency. The electrons are ejected instantaneously, that is, there is no time interval between heating of metal surface by the light and the ejection of electrons. The kinetic energy of emitted electrons depends upon the frequency of incident light. The number of electrons emitted is proportional to the intensity of incident light. According to classical theory, the energy of light depends upon its intensity. Thus, if the surface of metal is supposed continuously to the light of any frequency, the electron should keep on gaining energy, and ultimately the energy should become so high that the electron should leave the metal atom. But actually this not happen. However, Einstein explained different observation about photoelectric effect by applying Planck's quantum theory. According to this theory, each quantum of light called photon has energy equal to h nu. When photon hits the metal atom, it transfers its energy to the electron. Energy equal to threshold value is used up for bringing about ionization, and remaining energy is converted into the kinetic energy of the electron. The quantity h nu naught is called work function and is equal to the ionization energy of the metal atom. So h nu is equal to h nu naught plus half mv square. The frequency of incident light is equal to threshold value. Electron will be emitted without any kinetic energy. Intensity of light means the number of photon hitting the metal surface per unit time. Thus, increase in intensity increase the elec- number of electron emitted, but will have no effect on their kinetic energy. So the equation can be written in the form: kinetic energy is equal to h nu minus h nu naught. This equation shows the kinetic energy of electron emitted varies linearly with the frequency of incident radiation. Thus, a plot of kinetic energy of emitted electrons versus frequency of incident radiation will be a straight line with slope equal to Planck constant, that is h. This gave one of the method to find the value of Planck constant. Origin of quantum mechanics. In view of the failure of classical mechanics to explain the phenomena associated with the small particles, a new mechanics has been put forward to explain these phenomena. One of these is called the matrix mechanics, put forward by Heisenberg in 1925. It is purely mathematical and does not assume any atomic model. The other is called the wave mechanics, put forward by Schrödinger in 1926. It is based upon de Broglie concept of dual character of matter and thus takes into account the particle as well as wave nature of the material particles. However, it has been shown that both mechanics are essentially equivalent so far as the basic physical concepts are concerned. Wave mechanics being comparatively simpler and more useful in application to chemistry will be discussed in the present chapter. It is also called particle mechanics or quantum mechanics because it deals with the problems that arise when particles such as electron, nuclei, atom molecules are subjected to a force. The branch of science which takes into consideration de Broglie concept of dual nature of matter and Planck quantum theory and is able to explain the phenomena related to small particles is known as quantum mechanics. The heart of quantum mechanics is an equation called Schrödinger wave equation. It can be derived directly on the basis of certain postulates of quantum mechanics. Thus, our main aim in the present chapter will be derive Schrödinger wave equation directly as well as on the basis of postulates of quantum mechanics to study certain results that follow from Schrödinger wave equation. Some applications of Schrödinger wave equation. After that, comparison of classical mechanics with quantum mechanics. Classical mechanics, it deals with microscopic particles. Quantum mechanics deals with microscopic particles. In classical mechanics, it is based upon Newton's laws of motion, while quantum mechanics takes into account Heisenberg's uncertainty principle and de Broglie concept of dual nature matter. Classical mechanics is based on Maxwell's electromagnetic wave theory, according to which any amount of energy may be emitted or absorbed continuously, while quantum mechanics is based upon the Planck quantum theory, according to which only discrete value of energies are emitted or absorbed. Classical mechanics explain the state of system is defined by specifying all the forces acting on the particles as well as their positions and velocities. The future state can then be predicted with certainty, while in quantum mechanics it gives probabilities of finding the particles at various locations in space. Now, the relation between quantum mechanics and classical mechanics. The relation between quantum mechanics and classical mechanics is found by observing the condition under which quantum mechanics gives the same result as classical mechanics. When the velocity of macroscopic body is much less than the velocity of light, quantum mechanics gives the same results as Newton's classical mechanics. When the Planck's quantum approach the limit 0, the time-independent Schrödinger wave equation reduces to Newton's second law. When the system is in highly excited state, if the value of principal quantum number n is very high, both mechanics gives the same results. It is called Bohr's correspondence principle or principle of complementarity. After that, de Broglie dual nature of matter and radiation. It was suggested by Newton that the light is a stream of particles which are photons or also called as corpuscles. In other words, light is corpuscle in nature. However, this concept failed to explain the phenomena of interference and diffraction, which could be explained only if light is considered to have wave nature. But at the same time, it was observed that the phenomena of black body radiation and photoelectric effect could be explained only if the light is considered to have particle character. Hence, finally, it has been concluded that light has dual character. Louis de Broglie, a French physicist, in 1924 advanced the idea that, like photon, all material particles such as electron, proton, atom, molecule, a piece of chalk, a piece of stone, or an iron ball that is microscopic as well macroscopic object also possess dual character. The wave associated with the particle is called the matter wave or de Broglie wave. The de Broglie relation. The wavelength of wave associated with any material particle was calculated by analogy with photon as follows. In case of photon, if it is assumed to have wave character, its energy is given by E is equal to h nu, where nu is the frequency of wave and h is Planck constant. If the photon is supposed to have particle character, its energy is given by E is equal to mc square, where m is the mass of photon and c is the velocity of light. So h nu is equal to mc square, and we can also put lambda is equal to h by mc or lambda is equal to h by mv. mv. De Broglie pointed out the above equation is applicable to any material particle. The mass of photon is replaced by the mass of material particle, and the velocity c of the photon is replaced by the velocity v of the material particle. The above equation is called the de Broglie equation, and lambda is called the de Broglie wavelength. Thus, the significance of de Broglie equation lies in fact that it relates the particle character with the wave character of matter. Significance of de Broglie equation. Although the de Broglie equation is applicable to all material objects, but it has significance only in case of microscopic particle. Thank you. That's all from my side.